All right, so we are going to pick up where we left off last time. And we're going to look at the last point that I was making about standard errors and R-squared, just to kind of drive this point home. So we're going to repeat our examples from last time. We're going to do something like this. So here we are generating random x points, creating this deviation or error term, and then defining our y through this relationship. Same thing as last time. And I'll just quickly put this together in a table. And we're going to regress y on x using that table that I had just put together. And we should be able to make a summary of this to see the regression results. So I'll run through all of this very quickly. And you'll see something like this, like before. And just remember to note that when you copy this code, that it will probably appear a little bit differently for you because the random draw will lead to different data points on your computer. So this is our example one. Oops. And for our second example, we're going to do the same thing, except our error term is going to be multiplied by 2. So it'll be twice as big. And I'm going to do the same thing here, set up the table. And we can do a second model run on this one. Okay. So I know you guys are probably typing this down as well, but in this one, right, we have this difference where my error term is twice as big. So generally, what would we expect in the summary? What would be different? The R-squared will be lower, that's right, because our errors are higher, and so the variation, less of the variation from the error is being explained. Anything else? Yeah. Yeah, exactly. And how might they change? Yeah. So in fact, we can see here. So if I compare against my first one, 0.03688, here it is 0.07376. Exactly. I promised that I would stop using the base version of plotting. So here we go. We'll use ggplot. So if you guys remember from an earlier class, the way we set this up, we feed in the data, and then we put in our aesthetics, which is just telling you what you want to set on the x and y axes. In this case, x equals x, y equals y from our data table. I'm gonna make this a point plot, and then I'm adding this geom smooth, which is gonna give me the fitted line of the regression between X and Y. It's just a shortcut. Yeah, I will do that. I'm setting um, I'm setting this Y limit here as a way because I'm going to plot both plots. And so this is letting me fix the plots next to each other. So we'll call this plot 1. So if you want to see what this looks like, you can see it plotted here. So what I'll quickly mention is that you see the points are in the data that we generated. The blue line is the fitted value. And then this shaded region around here represents a confidence interval of our slope value for the coefficient. Remember that the standard error is essentially telling us that this mean estimate essentially has some, we'll say, uncertainty around it, right? And that mean value can take on sort of other values. And if you do that many times, you can see the shaded region representing, I believe this should be a 95% sort of confidence interval. Okay. So I will go ahead and plot the second value. So data equals for model.2. And we'll just do the exact same thing. Okay. And the package cowplot that I had included up at the beginning, you may not have this installed, in which case you can do that when you get a chance. This is a nice little add-on feature for ggplot that lets you do a lot of customizations in ggplot. And the one that I'm just using here is just letting me plot a couple different plots side by side, just so that we can see. So that'll look something like this. Oh, I didn't save it as a plot. So you can see basically what's happening is that all of these points get pushed out farther because we've multiplied our deviation by 2. And you can see that because of that, the size of the standard error increases, which will in turn sort of increase these the confidence interval, the width of that confidence interval, right? Which makes sense, right? Your points are more spread out, so your estimate of the exactness of that slope is a little bit wider in its uncertainty. Okay, so I'm gonna do something kind of interesting here now. I'm gonna create a function to manually calculate the standard error. And so this is already happening automatically in the LM function, right? It's generating these numbers for us. But we'll just create this function for now, and we'll see what happens. So I know I said you didn't need to memorize this, but here we're actually going to use that equation that I talked about before. So this is the sum of y minus y hat squared divided by n minus 2. So something like this. Oh, I need to put parentheses around that. And the denominator for that calculation is x minus the average value of x squared. And our output is the square root of those values. And we'll return our output. And next, I'm going to also manually calculate the r squared. So this is going to be a similar custom function. We need x, y, and beta as our inputs. And numerator is, again, the y minus y hat squared, not times 2, sorry. And our denominator is going to be y minus the mean of y squared. Oops. And our output is 1 minus the numerator divided by the denominator. And we'll return that. Okay. So these should give the same values as a summary. Actually, might be slightly different because I actually didn't include the intercept, but it's okay for all intents and purposes. They'll basically be the same. We happen to know the intercept is 0. In the estimates, it's not quite going to be 0, but it'll be close enough. So we'll get a value very close. So actually, I want to take advantage of the fact that we know the true value of our coefficients, right? So what is beta? What should beta in truth, universal truth be for this particular example? Same as last time. 0.5, exactly. So we're going to do something a little bit interesting here. I'm going to purposely modify to an imperfect beta. So using my manual function, I'm going to calculate the standard error, the standard error, assuming that the beta is not 0.5. And I'm going to use the same thing for r squared, xy, and give it a fake incorrect beta of 0.45. But then for example 2, I'm going to modify to the perfect beta. Okay, so let's go ahead and run these and we're going to see what happens. Okay, so we can see that the standard error for the coefficient here, it's still relatively close to what was originally estimated in the R-squared value of about 0.6. And then in the second one, um, your standard error is twice as large and the R-squared is only 0.26. So the point here being that as a metric to demonstrate how good the model is, right, at sort of ground truthing the true value, our standard error and our R-squared, like these are both better in the incorrect beta than it is in the correct one, right? And so relying on these values without knowing the context of your problem and the context of the data may lead you to some conclusions like the fact that this model is better than this model, better, whatever that means, right? When in fact we know that this is not correct. Any questions or confusion? So this is kind of a follow-up to that last example as well with the Anscombe quartet, right? About how these values can be maybe deceptive if you're using them incorrectly, right? We really need to think about the context of the problem when sort of deciphering standard errors and R-squared and what that means relative to the model. Like these values are sensical in this like statistical interpretation of them, but as a way of saying that this model is better than another model, you should not be doing that when you're thinking of these values. Okay. So how do we go about thinking this question of how good a model is, right? So we've talked about standard errors and R-squared. And today we're going to introduce a couple of other things to think about when considering sort of the goodness of a model. But taking a step back, really, you should be thinking this holistically across many sort of different sets of measures. Okay. Let's jump on over to some notes. All right. So one concept that we've been talking about a fair bit are the errors, or also known as residuals. Okay, so as a quick refresher, residuals, these are the deviation between observed value and estimated value. Right, so this is how far away any particular point is from our fitted line. So if I were to draw a plot of y, and x. All right, let's see if I can do this accurately. Let's say I have something here, here. And I have a line like this. So the residuals would be something like this. So if these differences are, okay, hang on. So let's say this is 1.5 and this is 2 and this is 1. And we'll say this is our -2, -3, negative, oops. This is 2.5. So that's like the size, that's the actual residual value. So the way that I would plot what is known as a residual plot is a y hat versus my residual value. Okay, so let's say this point here corresponds to A, B, C, and so on and so forth. So then I could divide this up something like this, A, B, C, D, E. And then I would match the corresponding values. So at A, right, this would be this value here. That would be 1.5. So actually, let me draw some axes on here. -1, -2, -3, 1, 2, 3. So my A point would be 1.5. My B point over here would be -2. And so on and so forth. So C would be, let's see, 2.5. Next one would be -3. And the next one would be 1. Okay. So this is like a simple example of how a residual plot is put together, right? Um, we essentially figure out what each of the error terms are and then plot them against the actual y values in against the fitted piece that you're comparing against, and that will give you this like distribution of errors across the uh, predicted set of points that your model is predicting, right? Which is, each of the corresponding y points along this line. Any questions about how I'm making this, or if this isn't clear? Okay, so why is it important? Why do I care about looking at something like this? So let's ask a question. So, okay, hang on, I'll just write. So residual equals observed minus predicted. So let me give an example. So y hat and residual. 0. Okay, so let's come up with a hypothetical residual plot that looks something like this. What do you guys think about this? Huh? Excellently drawn. Well, besides my artistic ability, what do you guys think about this? Yeah. Yeah. So that's exactly right. So if you think about this relative to, let's just say this is a one-dimensional thing. So our error is 0 here, right? And I draw a line over here. So every single value here, every single residual value is positive. So you have all positive errors. So this won't translate exactly, but that means that in your XY plot, that would mean all of your points would be above my fitted line, right? Does that make sense? So the residual plot is actually a really powerful tool to diagnose things like biased fits. So you might ask, okay, well, why don't I just look at X versus Y instead of looking at the residuals? So you could do that in this particular example, and in fact, it would be very obvious, right? But one of the nice things about the residual plot is that you are looking at your ultimate fitted value against your errors, which means that this can accommodate any sort of number of dimensions. So while we are currently working in the world of like one X variable, right, you can imagine that if I had 10 of these, like you could no longer do a diagnostic by looking at my X's versus my Y's. And so really, this is the visual way that we are able to do that in a multi-dimensional sense. And that's why this is a really sort of powerful visual tool. Yeah. So hopefully you guys can see the fact that this is like very sort of obviously biased, right? All the errors are positive, which means that in this case, they're all above the line. There are other things that that the residual plots let you diagnose as well. So let's suppose we have one that's slightly different. So we have our y hat here and our residuals here. And let's say our 0 point is there. So what happens if I have something like this? What do you guys think? Good or bad? And think about what the plot would look like in our corresponding XY space, if this is just like a one-dimensional bit. Yes.
If we're simply counting the number of data points above and below, it's probably slightly, if there's 5 points, probably 4 points roughly there.
Okay.
I mean, the things are like on upward equally on 0.
Sure. So that's one thing that you're kind of pointing out to look at. But okay, help me out here. What would the what would the what would the fit look like on X and Y?
It would be like ever so slightly like, I mean, if I'm simply looking at the number of points, and there's more positive points than negative points, that's going to be slightly, ever so slightly.
Well, so they're about the same, right? You've got like 5 below and 5 above. But then what is it? What do you think this plot will look like? Yeah.
On the end.
Yes. And more specifically, is there a pattern to that? Yeah.
Possibly the wrong order. Fit.
Yeah, so that's right. Although, we'll get to like that fit type of thing a little bit later. But I guess the point is what you see is that here I have negatives, then a bunch of positives, and then a bunch of negatives. So this is essentially what you're saying, but let's try and look at this more explicitly. So suppose my line looked like this. It would mean my first two or three are going to be negative. So I'll have something like this, right? Because it's big negative, smaller negative, and then almost zero. And then positive errors, right? So smaller error, bigger error, even bigger error, and then coming back down. Something like this, right? So in this particular case, it just so happens, right, that the shape kind of looks the same as the distribution of the errors. And so now looking at the spread of the data, like, do we think that this is a good fit? It might be like a different order kind of fit, right? So thinking about that, what would we say the like ideal residual plot should look like then? Yeah. Yeah, exactly. Exactly. So a more randomized set of residuals means that, right? So kind of what Peter was saying before is that the points are equally distributed above and below. They're not all on one side, and they're not systematically on one side and another side. So if these are just kind of randomly scattered about, that's kind of what we're looking for in the residuals. And so anytime I plot a residual plot here, and I'm seeing some underlying pattern, that's telling you that there's probably something in your model that's like biased or incorrect in some way, right? And so these residual plots are really a great way of supplementing, other diagnostic tools to allow you to quickly identify whether a model is problematic or not. Okay. Yes.
So you have plot a thing of residuals, and it's not random. It looks like there's some pattern to it, right?
Yes.
Would then you would go back and adjust according to there was a degree of randomness annually or a degree of randomness by a test?
I would do both. I think the tests, especially for this type of stuff, is a way of reducing that information into some kind of digestible number. But really, like residual plots are pretty simple. You could look at them across almost any number of dimensions, and you could pretty quickly tell if there's like a line in your residuals or if they're like dispersed in weird ways. Yeah.
The plot on the right, does that indicate the x of the explanatory variable is not correlated with the errors in a way?
No, they are. They definitely are, but probably in a way that you didn't intend or not in like a correct way.
So if you try to run a, let's say, correlation between x and the error term, what would the relationship look like? If I were just plotting x and the error term to see if the residuals of the errors are in any way related to the explanatory variable?
Well, okay, I mean, in this particular case, all I'm gonna say is that like on average, y increases as x goes up because there's like a positive slope, right? On average, but
So with the error term, so I'm talking about the error term x and the error term.
okay, so correlation of x with the error term. In this case, you in this case, you might get tricked because it's probably like you could arrange it in such a way to be uncorrelated. Like it's not correlating x and the error term are not generally going to be useful. Let me think if that's true.
Not for all the conditions that the x should not have any information about the error term.
No, that's right.
Yeah.
Except that in this case, it's satisfying that condition, but it's not telling you anything beyond
Okay.
beyond that, right?
Good. Just to check that condition, is it a good idea to correlate x and the error term and see how the errors are distributed around conditional on any given value of x?
Yes. So that can be an additional check that you can do. Yes.
And it looks something like this, that the errors are pretty randomly distributed, conditional on any value of x.
Yeah, but again, that'll be more to check like the assumption of like a linear model fits with your data. I don't think it'll be, it's not really as a model diagnostic device as in terms of how good a model is, which is what we're talking about here.
But could it not be used to check the zero condition mean assumption to see if in any way the U term is determined conditional on the value of x?
Okay, yeah. So think about what that would mean. So if it is conditional on the error term, then what?
You find some sort of relationship with the error terms that say would either increase as x increases or decrease as x decreases.
Okay, and then what would that mean?
That the variance of the error term is being explained by x.
Okay.
And would that then violate the I'm not sure if it's heteroscedasticity or homoscedasticity.
Homoscedasticity.
Homoscedasticity assumption.
Yes. So then essentially what that diagnostic would be telling you is that you're probably missing something in the error term that you should be capturing in the model, or you can use some transformations, yeah, robust standard errors to like account for that, right? But that is like a separate category of issues that we're talking about, right? Because this is focused on trying to figure out if a model is good or not. What you're talking about is whether or not like assumptions of the model are being violated.
Would the goodness of the model also not include that you're not missing a lot of omitted variables? And if you have something that violates homoscedasticity, and then you're probably missing something in that error term that's being related to x, would that then suggest that your model is not a good fit because you're missing something?
Yes, but the nice thing about this is this will also tell you that.
Oh yeah, okay.
Right? Because if you're missing something fundamental in your model, usually that's going to show up in the residuals as some kind of systematic bias.
How would that look like in terms of what it finds?
It will be not random.
So having some relationship with the y-hat term.
Yeah. So that's exactly right. So it could come in any number of ways. Like you could see an increasing trend, a decreasing trend, a non-random distribution of your residuals across y. Like it might go like this, or it might go like that. Yeah. So I can't go through, I can't like cover all the ways that the graph would look, but this will help you capture that. Yeah. Okay. So just to sum up, the thing that you do want from your residuals is something like this. You want just randomly scattered data points that should be centered around 0. Okay, and so if you see a plot like this, you can say, yes, that's great. My residual plot looks wonderful. And I'm, happy with my model in regards to this diagnostic device. Okay. So a couple other, well, let me see here 1 second. Let me go back to here. Yeah, okay, let's go back to showing how we can look at some residual plots and how to generate those in R. So we'll shift back over to here. Okay. So a couple of other shortcuts. So there's a predict function. So who can tell me what you think this function does? So I'm inputting into the predict function the linear model, right? That linear regression that I've essentially saved in example.model1.
This gives you the fitted values.
Yeah, exactly. So remember that we have this vector x of 100 values randomly generated. We also have a vector y, which are the corresponding, y values to any individual x. So that's our xy data set. If I wanted to figure out, for this particular x, where on this line we are, or for this x, where on the line we are, you can use the predict function to do that. And so predict is spitting back y hat. Okay. And actually, I'll just call it that. We'll do it like this. Y hat is this. If I run this, I should now have a vector of points corresponding to each x. And I can even plot x and y hat. And what do you guys think will happen? No,
In
not.
Y hat, you have a bunch of integers and then you have floats.
These are just the 0.90, 0.91, 92, 93.
Looks like the index.
Yeah.
Oh, okay.
All right. I'm plotting my x and my y hat. What do you guys think?
You just get the fitted line.
Yes. Almost the fitted line. I'll get all of the points that correspond to the fitted line. So these are the predictions corresponding to each of my x's. Okay. And I can essentially use this predict function as a way of not only generating the y hats, but putting in new data points. So let's say I wanted to look at new.x. I can predict here, putting in the model, but then inputting new x data. And what this will let me do is, according to my fit line, figure out if my x value was 25, what would the value of y hat be? If my x value was 29, what would my y hat be, and 42, and so on. And so, I did not put x, there we go. And so here we can see 25, y hat is 12.3, 29, 14.1, and so on and so forth.
This is just applying the same equation as in model 1, but putting new x values in there.
Yes, exactly. One word of caution here is that we trained our model based on random points between 0 and 50. I've asked it to generate a point at 57. This is sort of out of bounds of where our model is calibrated. And so that's a warning flag to think about, where essentially this is kind of like predicting into the future, right? Or predicting sort of out of the bounds of where I trained my data. And so just as a word of caution, that's something to think carefully about if it makes sense to do. Okay. So I can add that as a column so that I can plot my y versus my y hat. This is how I add columns in data tables, but however you want to do it. Basically, I'm adding a predicted.y, which is my y hat. So when I look at my for model 1, if I were just to grab that really quick, somewhere around here, you have your x, you have your y, and now I have my predicted.y. And I can do something like plot against the original y's. So this is plotting y hat versus y. So that looks something like this. So for this type of plot, right, this is what I'm predicting. This is what's actually observed. So the closer each of these points are to this line, which is just a line of slope 1, then the closer the model is at estimating the outputs equal to the actual values. Yeah.
What happens when you remove the intercept equals to 0 condition?
This thing about what this line is saying. It's just saying do my observed equals my estimated, right? This isn't a fit. So we just want to slope one line.
Line of equality is so that when everything corresponds.
Yes.
Line.
Yes. Yeah.
Can you see this and you see okay, you want to take all the points that are closest to the line, or you've done a good job predicting, right?
Maybe, sure.
Maybe. How do you select which ones? What is there say, as close as possible, but within this mark, within this plus minus? You have to like when would you, I guess, pulling the thread on the question, like how much do you do this before you say okay, fine, let's get out?
Yeah, that's highly context dependent, but okay, let me back up for a second. What are each of these points sort of representing in terms of distance from the line?
The error?
Yeah, the error, exactly. This is just a different way of showing it. This is kind of a less traditional way of showing it. So really the question you're asking is like, when do I care that the errors are really big or really small?
So
That's
this show
yeah.
residuals.
Yeah. In fact, let's move on because I don't want us to focus on this plot because that. Let's take a look at the actual residuals. Okay, I'm going to create a table called segments. So this is x, y0 equals y, and y1 is equal to my predict actually, we basically already have this, right?
It's predicted of y.
So how would I go about calculating my residuals? What is the residual again?
Y minus y naught.
Yeah, exactly. So one way I could do this is residuals dot one, and I'm going to call this y minus y dot hat, right? Which I define, not dot.
You predict y and predicted y.
Yeah, so that's my y versus my predicted y. And that looks something like this. So I have 100 points that look like this. There's actually a shortcut for this. You can use resid similar to predict, and this will directly calculate your residuals. And we can see if I do this, it should be exactly the same, which it is.
Is resid base R? Or is it something else?
It's base R. So let's plot that. I'll do it outside of ggplot. Hang on. So for plot, this is going to be data table. We're going to have y hat is equal to predict of our example model 1. We're going to have residuals equals resid of example model 1. And in our data, we'll use this for plot table that we just used. And X is going to be our y hat. And Y is going to be our residuals. And we'll have a geom point. I'm going to throw in a horizontal line at 0, just to see if we are centered around the area that we want to be. And I'll put in some labels just so there's no confusion. Okay, so if I plot this, oh. Great. So do you guys see any underlying patterns in the data at all? No, it's pretty randomly scattered, right? We have decent number of points both above and below. And there isn't like a systematic way in which they're arranged going from left to right or up to, or bottom to top. So generally, I would say this is a pretty decent residual plot. Yeah.
Is there a metric for this, or just we eyeball it and say it looks pretty randomly scattered, and tell them, you know, one metric that says they don't seem to be correlated in any way?
You eyeball it. So we'll talk about some numeric things that we're going to do with residuals in a little bit, but as a visual test in itself, this encompasses a good deal of information that would be probably a lot trickier to capture in like some kind of like numeric metric.
Would a correlation coefficient be useful here? If you just correlate y with the residuals, maybe we get a really low value, like I don't know.
This visual is better because in a correlation one, if you just look at the number, I could devise residual plot, non-random residual plots that would have low correlation, which I assume is what you're looking for. Yeah, I could very easily do that. That would not be random. Right. So if you wanted to look at let's say correlation of y hat to your residuals, I could have points just straight up like this, and that would have no correlation, right?
Yeah.
And that would be a non-random. So like your ability to look at it visually encompasses like probably many like numeric tests that you could run on this. So it's easier to look at it visually. Yeah. What do you study? This is telling you whether or not your model is essentially biased in some way. So remember the example I gave where all of the points are above? That's saying that all of my error terms are positive. And so you're systematically under representing the true values of y. And so basically the residuals is a very, very powerful way of visually being able to see if there are problems in your model. Basically, if this plot is not random, you've got problems. No, yes, so it has to be the predicted y. because your regular y values are actually correlated with your residuals systematically. They're positively correlated. There's a proof for this that I won't get into, but yeah, has to be your predicted y, not your y's. Yeah.
Is calculated by the difference between observed and actual.
Yes.
And then why did you say is a value to predict the correlation between value and the y hat? I didn't get that.
Oh, I was saying, so there's a question of like, I can make this plot, but then are there just some kind of like number tests that I could run to see whether or not this is random? Okay. So like, in other words, can I just run a couple tests and look at the numbers rather than looking at this? And the answer is maybe you could, but this is like a lot easier. So one of the ones that was asked about is like if you could do a correlation between predicted y and residuals instead of looking at it. And you could, and it would tell you something, but I could come up with examples where I could distribute this non-randomly, but have a low correlation between y hat and my residuals, which is, I guess, kind of what you would be looking for.
By just graph the correlation between predicted y and value doesn't represent the opposite up there.
Yes, but if your y hat is systematically correlated with your residuals, you do have a problem, right? So let's say I have like a 0.9 correlation. That probably means something like my dots look like this, right? And then in which case I would say that's no good. But a low correlation between y hat and residuals doesn't necessarily mean that your plot is good.
Value. Do you refer to the this part?
The what? Sorry, can you say that again? I didn't quite hear. Oh, the AIC, is that what you said? Yeah. That is one other test. We'll actually talk about that one a little bit later. Yeah. But that's testing for something specific. It's actually not necessarily looking at the sort of general bias of the model. Okay. Anyways, so in addition to like R squared and standard error, we're trying to build our foundation for getting a better understanding of how to diagnose a model. And so this is one of the most fundamental ones not to overlook or forget about. Yes, this is a very powerful way of being able to examine whether or not there's a problem in the model. Yeah.
Could predicted y and residuals, in case where they're actually related, not randomly.
Predicted minus residuals.
Predicted and residuals. If
Okay.
The plot shares like a non-linear relationship that residuals increase increasingly as you go higher with the predicted y values.
Yes. And what would that tell you?
Your model gets
It's
worse.
it's heteroscedastic.
It's scholastic, but does it also get worse? Because as you increase your predicted y values towards higher end, your errors are much, much higher.
Yeah. So if you're basically saying if it looks like
Yeah.
this.
Yeah.
Yeah, that's a classic heteroscedasticity issue. And there are ways to like adjust for that. Yeah. Okay. There's also something called a QQ plot. Let me pull this up real quick. This is another diagnostic tool. This uses a package called QQ+R, which actually is probably not even installed on here. So let me do that really quick. Could not find function install package. Oh yeah. I feel like it's pretty rare where you're installing more than one package at a time, but okay. So actually, you don't have to use this necessarily. So the base version is actually kind of much easier. It's just y hat comma residuals. Oh, sorry, y hat. Oh, come on. Okay, hang on. You could do it like this. So that's the base version, and I'll just copy and paste the ggplot1 so that you have a reference to that. So it uses this QQ+R. So this will do the same thing. Looks like this. So QQ plots are a way to test whether or not your in this particular case, it's looking at whether or not the residuals are normally distributed around your predicted y, and that's generally kind of what we want. And so the closer it lays on this line here, then the better sort of that test is. So this is just like one, if you're having like a kind of hard time figuring out whether or not that they are sort of randomly and normally distributed around my 0 point, you can run a QQ plot to see that. And so it's decent, and at the ends you're going to have a little bit more variation, but generally I would say this is pretty good. So one extra test if you're having a hard time with the sort of visual aspect of the distribution around year 0. All right. Any questions? Yes.
The, how that trails off on the top and bottom,
Yeah.
that's because the X, are predicted, and then residuals. So is it because the predicted values went outside of the original model set, that instead of like 50 or something?
These ones won't really do that. It's just typically at the ends of your prediction, you have a little bit, there's fewer data points, so you have a little bit more noise, and also what it's calibrating against in a QQ plot. This isn't going to be too uncommon to see.
This is something you shouldn't worry about seeing.
Yeah, so if it's like totally off of the line, then you would be worried. Yeah.
Right now it's going towards the left at the bottom end and towards the right at the top end. It goes in the same direction on both ends. Is it good enough and bad?
Yeah, I would say as long as most of the line is generally along that slope, then you're okay. Okay, let's continue onwards. So the residuals themselves, the visual aspect of it does help, but there are some things that we are going to be relying on quite a lot in terms of numeric tests to think about how good a model is. So let's continue sort of talking about some of those. So there is something called a residual standard error. This is the standard deviation of residual values. So if you think about what that means, this is essentially asking what is the spread of points about the regression line. So the equation for this, which you don't need to memorize, but for your reference, 1 over n minus 2 times the sum of my residuals squared. So this is squaring them, but then taking the square root to kind of standardize everything. This is often compared to your mean value of y. And for some reason, it's not showing up. Did I lose internet connection? Of course I did.